Okay, hello everyone, and welcome to this presentation on Azure Durable Functions. So I'm doing this presentation as part of the virtual Global Azure event, and I hope you've been enjoying the event a lot. And I hope you've seen some really nice presentations done by all of our awesome speakers around the world. So some of you, if you've seen me presenting before, you've probably seen me presenting some kind of identity-related topic. This time I decided to instead present on Azure Durable Functions, which I've been using quite a bit recently at work, and I thought it would be interesting to share some knowledge on what those are and how you can use them. So during this presentation, we're going to be looking at a demo application, which will power an electronic signing workflow for electronically signing documents. And I thought that would be an interesting thing for you folks to see, because it has some reasonable complexity involved, and it's not like a hello world of durable functions. All right, so my name is Jonas Westlin. I work as a developer/architect at a company called Azure here in Finland. I'm one of the 3 Azure MVPs in Finland as well. If you do have any questions ever while you're developing something on Azure, do ask on Stack Overflow and use the Azure tag. It'll show up in my question feed as well as the feed of other very awesome people over there. On the left-hand side of the slides, you can also find my Twitter ID as well as the URL for my blog. So feel free to check those out. So during this presentation, we're going to be looking at what this electronic signing workflow looks like. So if you've never electronically signed a document, you'll understand what the general flow is like. Then we'll clarify some of the terms that we're going to use a lot during this presentation. So things like workflows and orchestrations. Then we'll look at durable functions, what it is, what you can use it for, and all these things that you should know. Then we're going to the demo. We're going to build this workflow using durable functions. And after the demo, we'll look at some more useful things to know, some kind of more, perhaps a little bit more advanced things as well. Then we'll have some conclusions and also a dedicated time for some Q&A. So if you do have questions, feel free to post them in the live chat at any time. I will be looking at it once in a while, and I can answer questions during the presentation as well. So just feel free to post your questions whenever you want in the live chat. And at the end of the slides, there's also a bunch of links to documentation as well as blog articles that I think are very awesome sources of information about durable functions. In the stream description, there's also a link to the slide deck. So if you want to download the slides, you can do that from there. And there's also a link to the sample application on GitHub. So feel free to check that out. So an electronic signing workflow. So if you've never electronically actually signed a document using many of the electronic signing services available, so the general way at a high level that it works is that there's going to be a user who uploads a document that they want some people to sign. And this service is then going to send an email to each of those signers asking them that, hey, this person has sent you this document. Please go here and sign it. Then the service is going to wait for all of those signers to respond. They might say, okay, I agree, I will sign this document. Or they might say, no, I do not wish to sign this document. Then if all of those signers sign the document, we'll create a signed version of the document that the first user uploaded. And then we'll send some kind of completion email to everyone involved, and the users can then download the signed version. So at a high level, it's something like this. This has been simplified quite a bit though, the actual signing services do have quite a lot more features than this, but for this demo's purposes, this level is enough. Now, about these words that we're going to be throwing around a lot during this presentation. So when you look for the definition of a workflow, this is one that you may find. So a workflow is an orchestrated sequence of activities that describes a process. So there are some activities that are executed in a specific sequence, and overall it describes a process. And an activity is essentially a step in a workflow. And when we talk about this context of workflows, and orchestration refers usually to the automatic management of workflows. Okay? So what on earth is this thing called durable functions then? So this is a framework that's built on top of Azure Functions and the Durable Task framework. So Azure Functions is the serverless platform of Azure. And Durable Task is essentially a framework for building kind of long-running tasks with a persistent state. So it kind of combines the two. It allows you to build serverless workflows using either C# or JavaScript. So these are the currently supported two languages. However, there is support for Python and PowerShell in the pipeline. So the team is working on those two at the moment. And if you feel like you have good opinions for the team on how they should implement those, do find those GitHub issues and let them know. But currently, today, only C# and JavaScript are supported. And so this goes a little bit against what you might do, for example, with logic apps. So logic apps, for example, allows you to build workflows with this kind of graphical style editor, mostly, and it's very kind of declarative. You declare the steps to happen, but durable functions is imperative in code. So that is the main difference there. And the reason it's called durable because it has persistent state. So under the hood, the workflow state will be persisted in table storage. And it allows the workflow to continue from where it left off, even if the function's host terminates. And under the hood, it also uses storage queues to trigger various things to happen. But neither of these things, the fact that it uses table storage or queue storage, isn't something that you need to care about. This is abstracted away from you. Now, currently, as of today, you can only use storage as the backing provider, but in the future, you may be able to plug in different providers for persistence and messaging there, so that, for example, you might be able to get higher performance with like Azure's event hubs, but that is not exactly possible today. There are three types of new functions that Durable Functions gives you. The first of them is orchestrators, second one is activities, and then lastly, there are entities. Now, entity functions we will not be looking at today. They are out of scope for this presentation. We will be focusing on orchestrators and activities. Now, you do need, in addition to an orchestrator, you do need an additional Azure function to start the process. So the workflow can only be started by another Azure function, but that Azure function can be of any type. Can be an HTTP triggered one, can be scheduled, queue triggered, anything. But you do need one, which we sometimes call the orchestrator client function or the starter function. So what kind of use cases is this thing meant for? Well, the simplest case is probably function chaining. So you want to do something first, then you want to do something else next, and then you want to do something else. So you want to do three things in sequence. You could do this with basic Azure functions. You could use queue triggers and queue output bindings to achieve a similar thing. But durable functions makes this quite a lot easier. Then we also have this scenario of fan out, fan in. So let's say you want to do a bunch of things in parallel and then do something once all those things are done. This is also something which is really, really easy to do with durable functions. And then one of the cases which is quite hard to implement yourself at least using pure Azure functions is external events and human interaction. So durable functions allow you to wait for events to happen in other systems. So for example, we could wait for a manager to log on and give their approval for something, for some process. And depending on whether they approved or rejected, we can do different things in our workflow. So you'll see this one in action in the demo as well. Then there's also the interesting case of monitoring, kind of continuous processes, where you want to repeat a process based on a schedule or based on some logic. And you can poll the status and then do something if the status changes, for example. So durable functions is pretty good at doing long-running tasks, whereas Azure Functions really is not meant for that normally. Okay. So we're going to be talking about orchestrators and activities today. So why the two? Why do we have two of them? So when you define an orchestrator function, that's where you're going to define your workflow. That's where the steps are going to be. And it is stateful. So when that orchestrator function progresses, that state is persisted in a history table. And it utilizes this tactic of event sourcing to build up its current state every time. And what happens is that when it continues the process, it's going to replay its own code. And you'll see this one in a bit, what this means. But because of this code replay behavior, orchestrator functions have this thing where the code that you write in them has to be deterministic. And we'll see what this means in a bit more detail a bit later as well. An orchestrator function, in addition, can also start sub-orchestrators and activities. Sub-orchestrators are basically other orchestrator functions which do some kind of sub-process, and activities are your steps in the workflow. They are allowed to do I/O, they are allowed to be non-deterministic, they can do basically anything that a normal Azure function could do. So when you have your orchestrator function running, when the code execution hits a call for a sub-orchestrator or activity, and you await in C# or yield in JavaScript that call, there will be a message posted to a queue in the background that is going to trigger that sub-orchestrator or activity, and that orchestrator function will be suspended. It will simply not run anymore. So the orchestrator is not waiting for those to complete. It is actually not running. So once a result is available from the activity, for example, there will be another queue message that then wakes up the orchestrator. This will cause the code to execute again from the beginning, but this time it will continue past that await or yield call. So it's using the history table to know that the activity was completed, and it has the result as well. So it knows that it doesn't have to execute it anymore. If you do need to check if your current code line is being replayed, there is a Boolean property on the context object that your orchestrator function gets. So if you do need to check that, it's possible. So the cases where you need to do that are quite limited. So let's look at a quick sample orchestrator function. So this is the kind of hello world of orchestrator functions. When you create a new orchestrator function, a new durable function in Visual Studio Code or Visual Studio, this is the function that you get. So we know it's an orchestrator function because it has this orchestration trigger attribute and the durable orchestration context as a parameter. So this function is pretty simple. It creates a list of strings and then calls an activity 3 times with different inputs. So you can see we use the call activity async function on the context to trigger an activity. And we also see that the activity returns a string. Your activities and sub-orchestrators can return results, and they do not have to be primitive types. They can be any types. And then the first parameter here, the first argument is the activity function name, and then the second one is the input to the activity function. And again, the input can be essentially any type. Once the activity function has completed, we put the result in the output list, and finally we return that as the result of this orchestrator. So in order for you to understand the replay behavior, I built this small animation here so you can see what happens. So let's say we start this workflow. There will be an execution started event. Then there will be an orchestrator started event, and we'll start running the code. So we'll start from line 1, initialize the list. Okay, cool. Then we get to the second line. Now we are awaiting an activity call. That means there will be an activity scheduled event, and the orchestrator completes. So you understand that the orchestrator is not running now. It has exited. The activity will run, and once it completes, there will be an activity completed event, and the orchestrator starts again from the beginning, from line 1. We initialize the list. Now when we get to the second line, it looks at the execution history table and sees that there is an activity completed event. So okay, we have completed this activity. We'll just get the result and put it in the list and continue. Now again, because we are awaiting an activity, there will be an activity scheduled and the orchestrator completes. So the same thing happens again. We go to the third line, call the third activity, and then it completes. And once the activity has completed for the third time, we start the orchestrator, but this time we go through all the lines, get the results, and return those results. Now you might be thinking that this is a little bit overkill for building an array of 3 strings. I think so too, it is. But what you must understand here, of course, that this is really a very simple example, and it's meant to show you how it works. And those steps could be way more complicated. They could run for quite a lot longer, for example. And the key thing here is that if we have completed the first activity, for example, and the function's host crashes completely, once it restarts, it can continue from where it left off. It will not execute activities which it already has executed again. So that is quite a nice property. Now, I noticed that I haven't received any questions in the live chat yet, but I did hear from my coworker yesterday that the live chat for some reason doesn't always show the questions unless you post something there. So I'm just going to post there quickly and see if that does anything. Or maybe it's all been very clear. That would be good as well. Okay, so let's continue. Oh yeah, I do see the test message now. Thank you very much. So because of that replay, because the code is ran again, right? So it runs again from the beginning. this property of determinism is required. And what it means is that with the same inputs, we always take the same code path and we always produce the same output. So with the same inputs to the orchestrator, it will always do the same things. So it cannot be dependent on things like time, for example. So for example, datetime.utc now in C# is non-deterministic, because it gives you a different result based on the server time. So if we were to replay the code that uses that, we'd get a different value each time it runs that code. And that would be kind of dangerous. Because when you replay the code and it goes to a different branch and calls, let's say, a different activity function, well, it's not really defined what happens, actually. It's most likely going to run in a bit of a corrupt state. And that's, not a good thing. Other things that you shouldn't be doing is, of course, random number generation, or GUID.NewGUID, which is also based on a random number generator. You should not be doing I/O or database queries or any kind of CPU-intensive computation, multi-threading, or thread blocking. So these limitations apply only to orchestrator functions. That last point of CPU-intensive computation, multi-threading, and thread blocking, that limitation isn't based on determinism, actually. That limitation is based on scalability, because orchestrator functions run on a limited number of hosts. So if you block that thread, you are blocking other orchestrator functions from running. So don't do that. So if you do need, for example, the current date time, there are some versions of some of these on the orchestration context object, like datetime.utc now and GUID.NewGUID. So you can use those, and they'll always give the same value even on replay. Now I do have a question. How does it behave if we have a loop of activity functions called in orchestrator function? That's a really nice question. So I'm actually going to go back a little bit. So here in our orchestrator function, we have a sequence. This is a function chain, right? So your loop, if you await the activity in here, so let's say you have a for loop that loops 3 times, and we call the activity inside that loop. It's going to be the same thing as this. It's going to be a sequence, essentially, if you await it inside the loop. However, we'll see in the demo how you can do it, that if you want to run them instead of a sequence, if you want to run them in parallel, I'll show you that in the demo. Now, kind of funnily, in an orchestrator function, you can do HTTP API calls with some limitations to the flexibility. You might be saying, hang on, I thought you just said don't do I/O in orchestrator functions. And I know I did. But the context object has a kind of deterministic version of running API calls. So you can use that in orchestrator functions. Okay, so then activity functions. They're the ones where you will do the heavy lifting. We know this is an activity function because of the activity trigger attribute here. And then here we have the input for this activity. And again, your inputs and outputs in activities and suborchestrators can be any type, essentially. But in this case, it's just a string. And this just returns a kind of a formatted string, which of course is a bit of a stupid example, because this is fully deterministic actually and could be run in the orchestrator. But you could imagine, doing a database query here and modifying the database somehow, for example. You can also do API calls with maximum flexibility and any other non-deterministic things. You can write files, everything. The results of activity functions are persisted in that history table. So when you return a result, that will be written to the history table, and then a queue message will wake up the orchestrator to let it know that, hey, a result is available. So I've made this small chart showing you what the workflow is going to look like that we are going to build in the demo. So let me just zoom in a little bit because I know that text is a bit small. So we're going to have two orchestrator functions. The main orchestrator here and the wait for signature sub orchestrator here. So the idea is that we have a sub process that is designed for waiting for a single user to sign a document. And the main orchestrator is in charge of the overall workflow. So the user is going to fill a form in a web application, and that's going to start the process. As the first step in our workflow, we're going to mark the workflow as started in the database. So this is something that isn't strictly necessary. This isn't something that you need to do, but in this case, we just want to know when the workflow has actually started. And then we'll send those emails to all the signers. And once we've done that, we'll start this sub-orchestrator for each signer. So if we have 3 signers, we'll start 3 sub-orchestrator instances. Now, when a signer wants to sign the document, we need to send an event to this orchestrator instance. In order to do that, our application needs to know the instance ID. In this case, the instance ID is random, so we cannot really know it in advance. You can actually assign it in advance if you want, but in order to send the event, the orchestrator has to be running anyway. So it doesn't really matter in this case. So as the first step, we set that instance ID to the database so we can send the events. And then we'll have it wait for that external event from that particular signer. And we're also going to have a timeout. So if the signer doesn't respond within 5 days, we'll just return a result that says that the signing expired for this signer. But if they do respond, we'll set that data to the database. For example, when they made this decision and if they chose to sign it or not. And once all of those sub-orchestrators are complete, we'll check, did all of them sign in the main orchestrator? And if yes, we'll create a signed version of the document that they uploaded. And finally, we'll send a completion email, which will also send if all of them didn't sign. And finally, we'll just mark the workflow as completed in the database and end the workflow. So you can see there's some reasonable complexity involved here. So let's go into the demo. So here in Visual Studio, I have the presentation branch of the sample app open, which has a bunch of things missing from the workflow. So we're going to be building this here. So if you do take a look at the sample app on GitHub, you'll see the full app there on the master branch. So in this solution, there's a bunch of projects. There is a web frontend written with ASP.NET Core, and there's also the workflows project, which is our functions app. Now, the first thing that we need, in order for our web frontend to start this orchestrator function, we need the orchestrator client function. So I have it here. And what this is a basic HTTP trigger Azure function. The only thing that is special about it is that it takes a durable orchestration client as a parameter, and it's decorated with the durable client attribute. That is something you have to do. And in order to start the process, our web frontend is going to send some data over there. So that's going to be in the workflow start model. That will include things like the signer email addresses, for example. Then as the next step, we'll start the orchestrator function. And we'll give that workflow start model as input. So the only thing you have to do is specify the orchestrator function name as well as the input, and that's it. Then as the first step in our orchestrator function, we'll want to get that input data. So we'll use the get input function on the context to get our object back. So in our orchestrator function, we have this durable orchestration context that you use to do pretty much everything in the workflow. And it has this get input function that takes a type, and then you get an object of that type back. The next thing we need to do is a database update. So we need to update the workflow started at time in the database. But if you remember, we can't do database updates in an orchestrator function because that's non-deterministic. And we don't want to do that every time when the code is replayed anyway. So we need an activity function. So I'm going to create it here in the same file. It doesn't have to be the same file. It just has to be the same app. So here I have the workflow started activity. So it's decorated with that activity trigger attribute, and it takes a GUID as input. It uses that GUID to find the signing request from the database using entity framework, marks the workflow as started, and saves the changes. So that's all that does. And then in our orchestrator function, we'll want to call that activity. So we use the contexts call activity async, give it the name of the activity, give it the input, and call that. So that's done. Now, because our activity doesn't have a result, there's no type argument here, and there's no result being taken here because it is purely a task with no result. Now then, we need to send an email to each of those signers that, hey, you need to come here and sign this document. Again, email sending isn't exactly a deterministic thing, so we need an activity for that. So this activity uses the sendGrid output binding to send an email. So this is just a standard Azure Functions thing. You can send emails using this output binding in. Okay. You're not seeing this in France. Well, YouTube says that the connection is excellent, so I do advise you to just restart the stream. So what we do here is that we assign this new message to this output parameter, and that'll send an email to a single user. But now we do need to send an email to a bunch of users. So let's do that. And because our activity supports only a single user, we have to call this activity a bunch of times. And so I mentioned earlier that if you do a loop and you await the activity call, that'll be a sequence. However, we don't want a sequence. We want these to just happen in parallel. So if we have 5 signers, we'll just send 5 emails in parallel. So to do that, we'll prepare a list of tasks. And instead of awaiting the task that we get, we just assign it to that list. And then once we're done with the loop, we await them all. And this is going to cause that fan out. So this is going to cause them all to run in parallel. Okay. So once we're done with sending the emails, we need to start the sub-orchestrator for each signer. So we'll do that. The approach here is very similar to the earlier one. So we want to trigger all of these in parallel. So we'll just prepare a list. we'll call the suborchestrator using call suborchestrator async instead of call activity async. Otherwise, it's the same thing, just a name, some parameters. In this case, we do have a result as well. And then we await them all. So now before we continue with the main orchestrator, let's go look at that suborchestrator and what it does. So it is here in the other file, still within the same functions app though. So this orchestrator function is not special in any way. There's nothing that makes this a sub-orchestrator. You can use any orchestrator function as a sub-orchestrator. The only reason it is a sub-orchestrator now is because we are calling it from another orchestrator function. And what we do as the first step is the same as in the main orchestrator. We get the input to this sub-orchestrator. Now the first thing we have to do in here, if you remember, we need to send an event to this sub-orchestrator. In order to do that, we need the instance ID of this particular orchestrator function. So we need an activity to set that in the database. So this activity just finds that single signer entity from the database and updates the instance ID and saves the changes. And then we just need to call it as the first step. It also doesn't have a result, so we don't need to worry about that. Then within this try catch, we're going to be waiting for the event. When you want to wait for an external event in a durable function, you use the wait for external event function on the context. You can give it a type as well if your event has some associated data. So for example, in this case, we need to send, for example, the information whether the user decided to sign the document or not. So it isn't purely about the event. We do need some more metadata. An event does need a name, that is required. And then optionally, we can specify a timeout. So here we specify 5 days. So if the signer doesn't respond, if we don't receive this event for 5 days, this line will throw a timeout exception, and which we'll handle here. And we'll return a expired decision in this case. Also note that we use the context.currentUTC datetime to specify when this decision was reached instead of datetime.utc now, since that would not be deterministic. One thing that I would like to highlight at this point is that when you wait for an external event, it is not staying here and waiting for that event. But same as with activity calls and suborchestrator calls, the orchestrator function exits after you do this. It is not running. It will just be in the database, essentially, be in the history and instance table. It just knows that this orchestrator is still waiting for this event. So when the event comes, the orchestrator function will replay from the beginning, and when it gets to this line, you will get the event. Same with that timeout. Now, if you do leave out the timeout, the wait time will be indefinite. It will literally wait for as long as the durable function exists. Typically, you don't really want to do that. You kind of want to control how long these things are. Now, the maximum timeout you can specify is 6 days, and that's actually a storage queues limitation, not a durable functions limitation. But if you do want to wait, let's say, 10 days, you can just wait for external event 2 times with 5 days timeout. You can totally do that. Now, in order to trigger this event, we could use the Durable Functions Management API, kind of HTTP API available when you use Durable Functions. which you can use to, for example, get the status of orchestrator functions. But in this case, we're going to use a slightly different approach. We're going to use another HTTP trigger function that our web frontend can use. It's going to send some data in there along with the instance ID of the orchestrator that the event targets. We use the orchestration client, the same client object that was used to start an orchestrator function. We can use that client to raise events. So we use the raise event as a async function, specify the instance ID, the event name, as well as some event data. And that's it. That will raise the event for this orchestrator. So now we know whether a user signed or didn't sign. So we need to store that in the database. So again, database update. So we need an activity. So let's do that. It's pretty similar to the previous one. It just finds the signer entity, updates a couple properties, and saves the changes. And then we just need to call that and return a result based on the event. It's pretty straightforward. So now if we go back to the main orchestrator. Now, once all the sub-orchestrators are complete, we will continue from this line forward. And we'll have all of the results from each of those sub-orchestrators. And the first thing we have to do is, assuming all of them signed, we'll want to create a signed document. Now, in order to do that, we need to do some computation, and we also need to store a file in blob storage. So we're doing I/O, which we can't do in an orchestrator. So we need another activity for that. So this activity is pretty simple. We only have a single service call. That service kind of handles the heavy lifting behind the scenes to create the signed document. So if you do want to know the details of what it's doing, just check out the source code on GitHub. Now we need to call it in our orchestrator. Now we will have a condition here that checks if all of the results are signed, then we'll call that activity. Otherwise, we will not. So you can have conditions, you can have loops. That is totally fine. You can do that, but it has to be deterministic. So because this condition is purely based on the sub-orchestrator results, it is deterministic. It is not based on current date time or whatever. And then we need to send another email. So we need another activity for that. So let's send the completion email to all of the users. So we'll say, hey, the signing workflow has been completed. Here's the link to download the signed document. And then we call that activity function again for each of the signers. We just want to do this in parallel. No reason to do it in a sequence. And then as the final activity function, we need a workflow completed activity. So we need to mark the workflow as completed in the database. And finally, we call that and return the results. All right. So that is our entire workflow. That is the whole thing. There's nothing else that is required. So let's run it. Cross our fingers for no demo effect. And see how this works. So I'm running this function app locally now with using the storage emulator. And once it has started, you can actually see those two HTTP trigger functions here as well. Those are the endpoints that our web application is going to use to interact with this workflow. So if we go to the web application, which I have running here, we can give our our signing request a subject as well as a message. So the idea here is that you can give some context to the signers on what it is that they are signing. So we can say something like, please sign this important business document. And then for the signer emails, I'm going to use one of mine twice, just with different plus IDs. So they are different emails, but the same email. And for the document, I'm going to use this very simple PDF. And we're going to submit that. And here we see the status. We see that neither of the signers has responded. We see the status is creating, so the workflow has not started yet. And we also see the workflow status here, which is from that management API. But now actually, if I refresh, we see the status is waiting for signatures. So the process is asynchronous, of course. So when the user reaches this page, the workflow hasn't yet been able to start. But now all of those sub-orchestrators, those two sub-orchestrators are waiting for that event. And that's why the status is now waiting for signatures. So I'm going to open up my email on this other screen and see that I have two new emails. And I'm going to just copy the first link and put it here. Here the user can download the document to see what it is that they are signing. And we can click sign or decline. I'm going to click sign. Now again, though, because the process is asynchronous, we sent the event, but the sub-orchestrator didn't have a chance to run yet. So we see that this signer has not responded. But if I refresh, then we see that this user has signed. And then if I open up the other link and click sign, we'll again see that, yeah, they haven't responded yet, but if I refresh, we'll see that the workflow has completed and we can download the signed document. For some reason, actually, the status didn't show up as completed though yet, but now it does. So we see that the output of that main orchestrator is this. Okay. So let's continue with the presentation a little bit. So some more useful things for you to know when you build your own durable functions. Error handling is quite easy, actually. So you just use the normal try-catch blocks, around activity or sub-orchestrator calls, and you're able to catch any exceptions that are thrown in those activities. And then you can choose if you want to do a compensating action or if you want to actually rethrow the error and just cause the orchestrator to fail. And then if you have some things like database queries, which can sometimes be flaky, it might just fail because of some network issue, you might want to do a retry. Well, that's built in. So you can just put in a retry policy, say that I want to retry this 5 times with 10 seconds in between retries, and that's it. Now, monitoring of durable functions is not the best thing. Azure Application Insights works, but the end-to-end tracing, as you see in the screenshot, it doesn't work correctly yet. The team is working on it, but you can see that there's a sub-orchestrator running there for 2 milliseconds, but the activity call that it did isn't visible, and the main orchestrator that started that is also not visible. If you do want to do logging in them, so you can use the basic iLogger in .NET Functions. The context has this neat function for creating a replay-safe logger. Use that to prevent duplicated log messages, because the code is going to replay so you get the same log message again, which might be quite pointless. So you can use that. If you do build these functions with C#.NET, I do recommend you use the analyzers package because it gives you a lot of very useful warnings. For example, if you use like the datetime.utc now, it'll tell you, hey, this isn't okay to do in an orchestrator. And a bunch of other things as well. If your orchestrators and activities start to become complex, the general approach of divide and conquer that applies to many things in computer science works here as well. So if you have a complex orchestrator function, you can split it into sub-orchestrators and call them in a sequence. You can also split orchestrator functions into methods. So you can't just make basic C# methods. However, if you do that, use the deterministic attribute on those methods to extend the determinism checks there, if you use that analyzers package. If you have a very long activity function, it might be doing too much work, so you can split it into multiple activities and call them in a sequence. Now, updating durable functions is one of the hardest things that there is. Because when you deploy a new version, you have to think about those already running orchestrations. So when you have an orchestrator function that's, for example, waiting for an event, it is going to continue once it receives that event. But if the code changes from underneath it, that's basically a violation of determinism, because now it's going to do different things and it's essentially going to run in a corrupt state. So what can you do? Well, you can change the orchestrator function name and just have those old orchestrations never complete. Or you could create a new version of the orchestrator side by side as a new function with a new name and just delete the old one later once you know that the old version is no longer being used. Or you could deploy a new function app entirely. That's a bit extreme, if you ask me, but, well, that is also an option. You can also check the docs for more information on this topic. Now, activity function contents can technically be changed without violating determinism as long as you don't touch the contract of the activity function. So that's one of the hardest things, I would say. Now, for some summary and some takeaways for you. You can use durable functions to build workflows in code. If you do prefer using a graphical user interface, you can use, for example, logic apps, you can use Power Automate, things like that. They make it very simple to do things, but they're also a little bit less flexible. I tend to prefer durable functions for almost everything. It allows you to implement these things like function chaining, fan out, fan in, and human interaction quite easily. The API makes the abstraction quite nice to understand. Use orchestrator functions to build your overall workflow and call sub-orchestrators and activities. But remember, in an orchestrator function, your code needs to be deterministic. So it cannot do things differently when that orchestrator code gets replayed. For everything non-deterministic, database queries, heavy computation, all that, use activity functions and call them from your orchestrator. Monitoring is definitely a weakness of durable functions at the moment, but it is improving. I'm really looking forward to having end-to-end traces work. When you update orchestrators, be careful. Keep that in mind, that if you have existing orchestrator functions that have not completed yet, they will be affected. Now, we have some time for some Q&A. So I see that we actually have one question in the chat. So if an activity is work in progress, what happens if we want to deploy updated version of the same activity function? Well, I would imagine it would be kind of the same thing as if you had any function, really, any Azure function, and you updated the function app. So I'm actually not 100% sure on this. It's either going to crash or Azure Functions is going to wait for some time for it to complete. Now, for activity functions, keep one thing in mind. If your activity functions complete, if it completes, but the functions host crashes before the result is written to the history table, that activity function will run again because it doesn't have an event that it completed. So most of the time you'll want to prepare for that eventuality that your activity function might actually run again. So if you can make it idempotent, I definitely make it so. Okay, so any other questions? It's quite awkward in a YouTube presentation, because in a real presentation, people would be just raising their hand immediately, but YouTube creates this 15-second lag, so you won't even hear my question until 15 seconds later. What happens if there is disruption to the underlying storage service? Well, that will most likely cause your orchestrator function to crash, or anything really. So it is going to cause a crash in the functions. That is actually a really good question, and I don't really have a very good answer for it. I've had some crashes happen before, and those orchestrator functions have actually then just continued once the storage was restored. But I'm not sure if that's the case in all cases. So I would kind of believe so. I would have to somehow test that, but that's quite hard to test. Maybe locally I could test it by crashing by just crashing the storage emulator, I suppose. Really good question, but I'm sorry, I don't really have a very good answer for that. Okay, well, if you do have more questions, feel free to post those questions to me on Twitter, for example, and I'll try to answer them. And so in the second to last slide, you'll find some links. So the first link there is the link to this slide deck. And then there is also a link to the durable functions documentation. I especially like the concept section there. It's really fantastic, actually. It explains things like how durable functions scales and how it all works under the hood really well, actually, with a lot of nice pictures as well to explain it visually. There's also a couple blogs which I like, which have some nice articles on durable functions, and there's also a link to my demo app. Now I do have one more question, so I'll just take that. Do you implement Azure pipelines in this process to automate deployment of your durable functions? Example of high availability architecture. Okay. Do you implement Azure pipelines in this process? Yes. So the same as any Azure function, you can deploy them from Azure pipelines or GitHub Actions, anything. You can totally automate the deployments. So with functions, be sure to use at least .NET functions. Be sure to use the zip kind of run from package mode. It'll work best. High availability. Well, the documentation talks about that quite a bit more, honestly. So do check the concept section there. They do talk about that as well. For high availability, you may need to run a second function app in another region, for example, so if a region is down, you can run your workflows in the other one. And as for performance as well, which kind of relates to that, by default, durable functions will use the same storage account as the Azure function. Now, if you want maximum throughput, you'll want to make a dedicated storage account for your durable functions, then in the host.json file, you can define which connection string it should use to connect to storage. So that's definitely something that you can do. But otherwise, yeah, so durable functions, the workflows are very dependent on that storage being alive back there, read and write. So the main thing that you can do for high availability is just replicate the whole function app in another region, I would say. Okay, cool. Yeah, if you have any more questions later, do send them to me on Twitter. Thanks for attending this presentation, and I hope you have a fantastic virtual global Azure.